We looked at the basic inverse trig functions, but how do we draw a general one? So let's try this one. Y equals 5 times the inverse sine of x on 3. Now basically I've just got to work out the domain and range and then fit, in this case, an inverse sine curve into that. Now I know the normal domain for y equals inverse sine x goes in between -1 and 1. So the difference here is x on 3 is going in between -1 and 1. Multiply by 3, I get my domain. X is in between -3 and 3. I can do a similar thing with the range, but remember this 5 is actually grouped with the y. So instead of saying y is going in between, well, for inverse sine it was minus pi on 2 to pi on 2. Now we'll say y over 5 is going in between minus pi on 2 and pi on 2, giving us our range. So then drawing it, if I'm only going to draw one curve, I can pretty much draw the same curve every single time. I just got to change the labels on the axes. So domain -3 and 3, range 5 pi and 2 minus 5 pi and 2, drawing an inverse sine curve, and there's our picture. So of course if you've got a math aid it becomes real easy, because you just turn your math aid on the side and there's your curve. This one's a little bit different. Inverse tan of the square root of 3 minus x squared. Domain. Well, normally for inverse tan it was all real x. However, we're actually substituting into the square root of 3 minus x squared, which has its own problems. You just can't find the square root of a negative number. So we've got to look after that. So 3 minus x squared has got to be greater than or equal to 0. This particular curve will go in between minus root 3 and root 3. Okay, now if you think of the normal inverse tan curve, it goes in between minus pi and 2 and pi and 2. But we're stopping at root 3 and minus root 3. So the question is, what are those y values that we're stopping at? So when we have restrictions on the domain, certainly in a symmetric graph where you have a look for the endpoints, when x equals root 3, inverse tan turns to be 0. The other endpoint is also 0. So that's not really helping me for my range, because we're going to start and end at the same y value. But it is a symmetric graph. So our logic says, let's have a look at the middle as well. Let's see what happens there. So at x equals 0, we get up to pi on 3. Okay. So it looks like my range is going to be in between 0 and pi on 3. Let's draw that. Pi on 3 minus root 3, root 3. And there we go. Inverse tan of the square root of 3 minus x squared. The inverse sine of sine x. Now, it will be based on y equals x. Now, the domain, sine x instead of x is going in between -1 and 1. So when is sine x in between -1 and 1? Always. So the domain is now all real x. Well, so maybe it is the line y equals x. However, it's still an inverse sine function. So we know the range, yeah, it's our normal range of minus pi and 2 to pi and 2. So hang on, let's draw this. So it's all real x, so let's mark it off every boundary value, pi on 2. Now y equals x, and we're stopping at minus pi and 2 and pi and 2. But we know the curve keeps going. So what have we got? We got a zigzag. Right? We're going to have an x-intercept again here at pi. You go back to the function. Sine of pi,
0.
Inverse sine of 0. So every multiple of pi is going to be an x-intercept when we plug it in. And so we're going up and down, like a sine curve, but this time it really is like dot to dot. We draw straight lines, because it's based on y equals x. Well, what about this one then? The sine of the inverse sine of x, so we do it the other way around. Domain. Domain normally for a sine function is all real x. But before I can find the sine, I'm substituting into inverse sine, and I'm limited into what I can substitute into that function. So it takes on the domain of inverse sine this time. So instead of being all real x, it's just simply between -1 and 1. The range, well, when x is 1, we get 1. When x is minus 1, we get minus 1. I don't know, did I bother with 0 or not? I mean, we know it's based on y equals x. So logic is sort of saying 0. Oh yeah, I did check it just to make sure. X equals 0, we get 0. So this time, we just have a piece of y equals x. But notice the endpoints of the domain and range now are not the pi on 2, it's now 1. So, boop, there's the sine of inverse sine x. So we don't get the zigzag for that one. That is all.